Okay. Hello, everyone. This is Adel, and I'll be the moderator of today's webinar titled Oil Well Modeling through Prosper, presented by our instructor, Engineer Amr Hilal. Engineer Amr is experienced production technology engineer with over 8 years history of working in ESP, Saccharod, and PCB systems. He has a strong experience in technical support for rig and rigless operations in coordination with service companies for job planning and implementation and monitoring. He is also skilled in artificial lift and production design through nodal analysis using different softwares like Prosper and Python. He is experienced in-person and online instructor for various topics of production engineering, like nodal analysis, cased hole logging, perforation techniques, and so on. Before we start our session, I'll just make a small presentation about OPA upcoming services and plans. Here is our next wave of quarter courses. We have 5 courses on conventional reservoir that will start tomorrow. Integrated production optimization that will start next Sunday, that will be presented by the same instructor of today's webinar, Engineer Amr Hilal. And AI drilling in 2nd of August, seismic attribute in 13th of August, and stack pipe in 13th of September. Here is a package discount on our wave. Buy 3 courses and get 2 for free. You will just enroll in the 5 courses for $500 instead of $800. So it's super discount. Make sure you enroll in it. Here is the course that will start tomorrow on conventional reservoir characterization, evaluation, development, and recovery. It will be 1-week course starting from tomorrow. So scan this QR code to register. And if you have any inquiry about the content or the outlines of the course, I'll be happy to assist you. Here is also another course, another live course that will start next week. It's integrated production optimization using nodal analysis. It will start next Sunday. This course will be presented by the same instructor of today's webinar, Engineer Am. You can also scan this QR code to register. And if you need any help through the content outlines, I'll be glad to assist you, or just contact us through any of our social media channels. Okay, here in OPA, we have provided more than 50 live course, which is converted now into recordings and available as recording courses sales in different disciplines like reservoir engineering, production technology, rig and rigless operations, G&G, data analytics and safety, and so on. You can also scan this QR code to register. I'll send, if you didn't catch up the scan, I'll send every link through the chat. So don't worry if you didn't scan. Okay. Here is one of our services, which is OP App Store, where you can access affordable alternatives for softwares, Excel add-ins for specific tasks, solve Excel sheets to resolve Excel sheets to save time and money. It will be a good alternative for the expensive softwares of oil and gas industry. You can check our App Store and buy any of our sheets. Here's one of our best services, which is mentorship program. It's a one-to-one mentoring sessions by highly experienced mentors. It's like a tailored program based on your needs. It's a one-to-one, as I said. You can request practice on how to produce output results from software, guiding on personal data, professional guiding for PhD and master, helping undergrad students in their projects. We have completed more than 50 mentorship programs with more than 950 learning hours. You can also scan this QR code to register in the mentorship program. Okay, when you visit our website, it's obacourses.com, you will find this homepage. You can access everything through our website, whether you are applying for online for recorded course or live course, enrolling in our free webinars, apply for mentorship program, or even apply for internship, or enrolling in app stores. You can access everything through it, so make sure you pay it a visit. And finally, how to be an OPA ambassador. There are two tracks. The first one is to take one or more courses with us or take a mentorship program. So what will you get? You will get discounts on all courses in the future and group discounts when you invite your colleagues. Thank you for listening, and now it's time for our session. Engineer Amr, you can share your presentation now.
Okay, hello everyone. Can you hear me?
Yes, we can hear you well.
Okay, fine. So, hello everyone. This is Amr Hilal. Adil has introduced me. So, I am going to just jump to the session. First of all, let's start with some PPT slides to introduce my session and webinar. We will talk about oil well modeling through Prosper. So oil well modeling is based on two sections or two segments. And as you all know,
Can you please open the slideshow?
fine?
Yes, perfect now, yeah.
Okay, so oil well modeling, as you all know, it is based on nodal analysis. As you all know, the flow starts from reservoir and going through the formation to this PWF point or the bottom hole of the well, and then up to the tubing and then to the separator. So we should divide these segments in order to be able to solve our problem and calculate or measure the total pressure losses across the system, and then we can calculate the total flow rate or operating flow rate of the system. So basically, we should first start with the inflow performance relationship. The inflow performance relationship represents the pressure losses across the reservoir, starting from the reservoir and to the sand face or to the completion. The simple equation for solving the inflow performance relationship is Darcy equation, which is represented by flow rate equals J multiplied by delta B, or the drawdown. The drawdown is the subtraction of the reservoir pressure minus the bottom hole flowing pressure. And the J, of course, which is the productivity index, and it is dependent on a lot of factors like formation permeability, skin factor, well bore radius and the drainage radius, the viscosity of the fluid you are flowing, and the net pay thickness. So its basic equation is the straight line IPR method, which is a relationship between the PWF and the flow rate. The PWF is on the y-axis and the flow rate is on the x-axis. And as you can realize from this graph, it is an inverse relationship in which when you are producing at lower bottom hole flowing pressure, you can produce more flow rate. And from this graph, you can deduce that the J, which is the productivity index, using the normal equation of the straight line IPR, you can deduce that the J, which is the productivity index, is the division of -1 by the slope of this curve. This is different kinds of inflow performance relationship depending on the fluid you are producing. Either it is water single phase or two phase, you are producing gas or not. You are exceeding the bubble point pressure of the reservoir, of the fluid, or you are below the bubble point. So depending on all of that, you can draw a graph or a chart for your inflow performance relationship. And this is a chart showing you when to use different kinds of IPR method, and I can share you after this webinar. And moving to the second segment of our webinar, which is the vertical lift performance or outflow performance. It represents basically the flow starting from the BWF point and up to the wellhead or up to the separator, depending on the end of the branch you are simulating against. So this relationship, we can realize that in the IPR, when you are flowing with lower bottom hole flowing pressure, you are producing higher flow rate. But in this VLP, you need higher PWF to produce more flow rate. And we can draw this vertical lift performance using Gilbert equations and the Gilbert charts, which is a representation of the pressure against the depth going down through the well. You have more and higher pressure, and going up to the well, you lose some pressure up to this wellhead, which is the intercept of this x-axis with the pressure curve. And as you know, there are different kinds of flow regimes when you are producing single phase or multi-phase fluid, because we normally don't produce oil only, but we produce water accompanying oil and some gases when you are flowing below the bubble point pressure. So different kinds of flow regimes you can realize during the flow, starting from the single phase flow down here when your pressure is exceeding the bubble point pressure, and going up with lower pressure, we can start to have some gas, and then different kinds of flow regime up to reaching the wellhead or the separator. And based on different kinds of regimes, you will have a different correlation for solving these pressure losses across the system. Okay, what happens here is we need to analyze the system and choose a nodal point which divides the two segments, and then solve the pressure losses before the node and solve the pressure losses after the node. And then from the two curves and the intersection between the two curves, this is the operating point you can flow the well at. This blue line is the vertical lift performance. As I show you that you need higher BWF to produce more flow rate. So the relationship is proportional, but the IPR, which is this violet curve, represents the IPR in which the bottom hole flowing pressure is lower when you produce with higher flow rate. And the intersection, usually it is the operating point at which you can produce your well. This also is the choke performance. As I told you, you can choose your endpoint is the wellhead, or choose your endpoint is the separator or the downstream point. In this case, there is another node which is the choke, after which and before which there is a difference between the flow rates and the pressure the pressure upstream and the pressure downstream, because major pressure losses happens across this choke. So this is the total graph that represents the system you are producing at. Delta P1 is representing the pressure losses across the reservoir. Delta P2 represents the pressure losses across the tubing and up to the wellhead. And delta P3 represents the pressure losses up to the separator. Okay, let's have a look now at Prosper and see how we can model a basic oil well. Okay, let's open Prosper. This is a portable version of Prosper. Everyone can use it at any time without installing or setting it up on the PC. Having a look first on Prosper, we have 6 main.
Excuse me, Engineer Omar.
Sorry, I didn't
Yeah.
share this screen. I will be sharing it right now.
Okay, no problem. Take your time.
Okay. Now everyone can see the screen of Prosper. Yes. Okay. Okay. Having a quick look on Prosper, we have 6 main windows. The upper left one representing the option summary or the intro of your well. To the right, there is a PVT input data, and the upper right one is the IPR data. Below here is the equipment data, and to the right, this is the analysis summary, and this lower right one, this is an intro or some information about your Prosper version. We usually don't use this. We just use these 5 windows. Okay, let's start. We are now having a new well. So let's start simulating. First of all, let's double click on this option summary. We need to simulate what? Oil and water, or dry and wet gas, or retrograde condensate. In our case here, we need to simulate oil and water. The method is black oil or equation of state or compositional model. We usually take black oil model. This is easier, and I can show you later what is the difference between black oil and compositional method. Our separator, we have just a single stage separator. Emulsion, no. The viscosity model is Newtonian fluid, not non-Newtonian fluid. About the data of the well, you are flowing through the tubing annulus or tubing and annulus. Usually we are producing through the tubing. The well type is producer, injector, or coal bed methane in producer. We are simulating a producer well. Artificial lift, you are here, you can choose your artificial lift method you are simulating, but in our case, we are going to use none, as we are going to simulate a natural flow well. Calculation type, we are simulating offshore well or onshore well. Let's choose on land or onshore well. The model will be rough approximation. We are not including or involving enthalpy balance inside our simulation. We are simulating the full system, of course, starting from the reservoir up to the separator. Let's keep the prime modeling as default. Well completion, here you can choose your completion. You are producing through a cased hole well or an open hole section. We are producing, in our case, through a cased hole section. The reservoir, you are producing from a single branch or multilateral well. In our case, we are producing through just a single branch. No gas cooling is involved in our simulation. If you are going to export a report about this model, you can enter your user information here, your company, field, location, well, and your name as an analyst. And here, by default, you can see the date of today or the time of your modeling. After entering all this data, you can click on Done. Okay, I usually prefer to go this equipment section as it shows in front of you right now. Let's double click on the equipment data. And before going through this, I have some input data to share with you. I will open an Excel sheet of an actual well. Let's see this data. I will share with you right now the screen of the Excel file in which the data of this basic well model is represented. Okay. Have a look now on this sheet of the well model that we are going to simulate. Here is the survey of the well. This is the PVT data, the GOR, the oil gravity, the gas gravity, and the water salinity. This is the IPR data, the type of the calculations you are going to choose, the productivity index, reservoir pressure, reservoir temperature, water cut, and total GOR. And this is the downhole equipment, number of tubulars you are using, and the casing size. So let's first go step by step to our model. I will return back to Prosper. Okay, if you double click on equipment data, here you have 6 sections below the equipment data. First of all is the deviation survey. And click on this square shape beside it. It will open for you this window in which you can enter your data, and you can realize that we have just 20 rows for entering the data. If you have a lot of rows inside your survey, you can use this filter button at which you can enter all the survey data and filter on it for the program to choose just the 20 points to represent your well. But in our case, we have lower than 20 rows. I will take them from the Excel sheet you have just had a look on. I will copy and paste the cells inside Prosper, and then you can realize that the program calculated the angle and the displacement of the well. After that, you can click on Done. Here you have entered the deviation survey. The second one is the surface equipment. In our case, we will be simulating a well at the wellhead. We cannot, or we don't use right now a choke. We don't need to make choke performance right now. So in this section, we will skip it for now. We didn't enter any data, so it is asking you some errors. You didn't enter the data. So we will click on this, Done, and then cancel. Okay, let's go to the downhole equipment. And here you are starting from the Christmas tree. Depth is 0. This drop down list you can choose. We have a tubing at 150, and its inside diameter is a 3/2 tubing. So this measure depth is 150, and its inside diameter is the inside diameter of the 3/2 inch tubing, which is 2.99. And the tubing inside diameter is by default. Then you have a subsurface safety valve. It will choose directly the depth of the subsurface as the end of this tubing. Its inside diameter would be 2.813 inch. After that, we have still tubing to 8,000 feet. and its inside diameter is still the same, 2.99. Then the casing to the end of the well, which we have entered inside the deviation survey, which was 9,275. He will be asking you the inside diameter of the casing, and let's assume it is a 7-inch casing, so its inside diameter would be 6.184. Now we have entered all the data regarding the downhole equipment. Let's click done. Going to the geothermal gradient. Now we should enter the geothermal gradient. The tubing head temperature or the surface temperature. Let's choose at surface at zero measure depth. Your temperature will be 60 degree Fahrenheit, and then at the
Excuse me,
end.
John.
Okay,
Sorry
what
for
happened?
interrupting you, but if you could share the Excel in the Zoom chat right now, because some people are asking for it so that they can practice with you, it would be perfect. If it's not ready now, okay, it's okay. We can share it after the webinar.
Okay, I can share it through the chat. Yes.
Yeah, Zoom chat.
Okay, I will take it right now. Just a few seconds. I will be sharing with you. Okay, now it is shared in your chat. Anyone
Yes,
can open it.
yes, we received it. Thank you.
Okay, thank you. And then let's move back to the geothermal gradient at zero depth. So we have 60 degree Fahrenheit at the depth of the casing or the reservoir depth. It is 210. Okay, degree Fahrenheit, and he will be asking you the overall heat transfer coefficient, or U in other softwares. Usually with oil models, we choose it to be 8, and then you can click on done after you have entered the geothermal gradient. Average heat capacities here, they are entered by default inside Prosper, and we'll click done. Gauge details here, this section is representing if you are using inside your completion a gauge and you know its measured depth. So it will take a label on this gauge, and during your simulation, it will choose this gauge and tells you what the pressure and temperature at this gauge depths, what they are at this depth. So it will be a label for you. Usually we use this for matching cases between the actual wells and the Prosper simulation. So in this case, we don't have a gauge right now, so we will click on done. You have entered all the data regarding this equipment data. After that, you can click on done. You will see that all the data you have entered are marked with true mark, and we have not entered any data about the surface equipment or gauge details. Also, you can see your completion is now drawn on the left. This is the shape of the subsurface safety valve, only the accessory we have used in our case. This is the depth of tubing and the depth of casing. And let me tell you something important, because Prosper usually takes the last depths you entered for the casing as it is the top perforation depth. So this is the perforation depth of your formation, and it is also representing the nodal point at which you are solving your model. Let's move now to the PVT data. From the data I have, it shows the solution gas oil ratio, or the total gas oil ratio inside this well or this reservoir will be 600. The oil gravity is 38 API degrees. And the gas gravity is 0.65. The water salinity is 230,000. We don't have any H2S, CO2, or N2. Let's keep the default correlation that the software using for calculating the bubble point and the viscosity. And now we have entered all the data regarding the PVT data. Now we can click on done. Now the PVT data you have entered, and let's move now to the IPR section. Here to the left, you can choose whatever the correlation you need to use to solve your model. PI entry, if you are knowing the productivity index of the well, you can enter directly the productivity index. Using Vogel will show you another window. Here, the software needs a test rate and a bottom hole pressure. And of course, all this correlation depends a lot on a lot of many factors. First of all, the reservoir you are producing. And secondly, the available data with you. You should choose the correlation that matches your available data. Let's choose in our case PI entry model because we know the productivity index, which is from the Excel sheet, is 1.5. The reservoir pressure was 4,000 psi, temperature 210 degree Fahrenheit, and water cut, let's assume the water cut is 10%. The total GOR is by default taken from the PVT data. Here the program has understood the total GOR and just has taken it from the PVT data. Okay, now we are ready with the IPR data. What should we do now? We should now calculate the IPR data and see the inflow performance relationship. Now we should click on calculate. Clicking on calculate, it will calculate for you the IPR curve for the well. Let's click on plot results to see the shape of the IPR. It will ask you what do you want to see on the curve. I need to see the pressure on the y-axis, and on the x-axis I need to see the flow rate. And then click on done. It will open for you the plot of the IPR. And here to the right, some data about the IPR. You can see that the absolute open flow, or this point, which represents the maximum flow rate or theoretical maximum flow rate you can produce from this well if you are flowing the well at 0 BWF. So in this case, it is around 4,000 stock tank barrels per day. The formation PI, we have not entered any skin on the well, so it is considered that no skin inside the well. and the formation productivity index is 1.5. Here is the input data you have entered for the IPR, and here are the calculated data. Okay. Okay. Now, and of course, the intercept with the y-axis, it is the reservoir pressure, as we all know. If you are producing zero flow rate, so the PWF is equaling the reservoir pressure, which is 4,000 psi in our case. Okay, let's click on finish and done. Okay, done. You can see that your IPR curve right now is represented on this right window. Okay, what we have done till now, we have entered the options summary, we have entered the PVT data, we have entered the equipment data, and we have entered the IPR data and draw the IPR curve. Now we need to simulate the vertical lift performance and do some sensitivity analysis on the system to know how the well will be flowing with different cases. So let's go to calculations and on system IPR plus VLP and click on it. Okay, here it has opened this window and the software will be asking you, you need to produce this well. So I will simulate for you what is the flow rate you are going to produce and what is the PWF or solution node pressure you will be producing with. So first of all, this cell highlighted in red means that your data is not entered or your data is not correct. But if they are green like this, so your data is correct. And if the cell is yellow, that means your data is on the borders or the limits. So what is the wellhead pressure or top node pressure you will be producing with? For example, if your network pressure is 500 psi, so the wellhead pressure for your well will be 500 psi, and let's enter this. And now we are ready to draw the VLP against the IPR. Just click on calculate, show calculating data, and then the program has just calculated for you the VLP against the IPR. This intermediate section represents the pressure traverse or across the different depths, different liquid rates, and the gas rate from the well, water rate, and all these data. To the right, this is the solution point, the liquid rate you can produce from this well around 1,900 stock tank barrel per day. The oil will be 1,700 because the water rate we have entered as 10%. The gas rate is around 1 million. The solution node pressure, which represents the bottom hole flowing pressure. And I forgot to tell you something here. The program is asking you what is the correlations you are going to use. So in VLP, we can choose among varied kinds of correlation based on your offset wells and based on the matching you have done before on other wells. And you have seen that the best correlations that representing your wells. So in this case, you should choose the best correlations that representing your wells. The default of Prosper is Petroleum X2, so we'll fix it for the time being. The software will be asking you what is the solution node you need to choose. So most often we use the bottom node, which is the PWF, to solve our problem. The rate method will be asking you if you need your curve to be linear or geometric. We will choose linear. And after that, click on calculate, and we have clicked on it. So let's move back to the right. The solution load pressure, which is BWF, the delta P of friction losses is around 60 psi's. The friction losses due to gravity is 2,140 psi's. And if you summing the friction losses and gravity losses and wellhead pressure, you will end up with the solution load pressure. Because in vertical lift performance, usually the PWF equals the gravity losses plus friction losses plus wellhead pressure. The total skin is 0 because we didn't enter any data about the skin. No losses across the perforation, no damage. And we can simulate other models with different kinds of input data to see the effect of all these parameters. And you can see a lot of data in this output table, like the wellhead liquid density, wellhead gas density, the first node pressure, which is the wellhead pressure. And you can see also the temperature at the surface, the interfacial tensions, and a lot of data. Okay, let's plot this to see the intersection point. Click on plot, system plot, plot all cases. It will be asking you what are you liking to plot. I will choose the liquid rate on the x-axis and the VLP pressure and IPR pressure on the y-axis, and then click on done. Now the program has plotted the IPR curve against the VLP curve, and the intersection point here, it is the operating point of the well. On the right, you can see some input data of the inflow and all the data you have entered before. Okay, now we know the operating point of the well and at which rate you can produce this well. So let's make something funny right now. We will do something called sensitivity analysis, choosing different variables and parameters, applying it as cases in this well, and see what will happen to the VLP and the IPR. Okay, so let's click on cases. For example, he will be asking you what is the variable you need to change. For example, let's choose the tubing diameter. The entered tubing diameter was 3/2 tubing. So let's see now what will happen if I am entering the 2/7/8 tubing, which is inside diameter is 2.44 inches. And 2.99, which is the inside diameter of the 3/2. And let's say choose 4.5 tubing, which inside diameter is around 3.9 inches. And now let's click on done. We have entered now a lot of data. The program will be asking you what is the first node and what is the last node. I'm asking you to simulate the tubing starting from the Christmas tree and the tubing up to the end of the tubing and continue. Now click on calculate, show calculating data. You have now the 3 cases you have simulated on. Let's step on this 2.44. You will see that the liquid rate or the operating point. Please keep in mind this figure is around 1,700. If you are using a bigger tubing inside diameter, the flow rate or operating point will be higher. And going to the 3.9, it will be even higher. So let's plot this and see. Now you have the three cases, the same IPR with the three different tubing. This one representing the tubing 2.44. So the operating point is lower in flow rate. This one is 2.99, and this one is 3.9. So it is simulating the tubing size against the VLB. So you can see that if you are using a bigger tubing diameter, you will have a higher flow rate or operating point. And of course, all of us know that this is not a proportional case, because when you are increasing your diameter up to limit, and then after this limit, the results will be against this low, the operating point will be lower than this. So let's, for example, choose a bigger inside diameter, let's say 4.5, for example, and then done. Continue. Calculate again. Show calculating data. Okay. 4.5. You will see that the flow rate now decreased. Yes, the flow rate decreased. So up to limit, and then after you increase the tubing diameter, you will see that the results are not the same. And if you are plotting this, let's plot this. You need to zoom on this chart. You can make like this. Okay, zoom again. You can see that this blue curve is the 3.9 tubing, and this green, this is 4.5. So increasing the diameter will increase the operating point and up to limit, and then again the results will not be the same, and it will be inverted, so the flow rate will be lower. Okay, let's simulate on another case. For example, let's remove this case, which is the tubing diameter, and choose water cut, for example. What will happen if you are choosing your water cut to be 0 and then 50% and 90%? What will happen to the intersection point? Done. And then calculate. Show calculating data. Okay. And then plot your curves. All cases. Done. Okay, what happened here? Okay, this is funny. Interesting. This is the IPR. This is the 3 VLP curves of different water cut. You can see that only one curve of the VLP is intersecting the IPR, and you can produce this well at this curve. And of course, it is the 0 water cut curve. If you are producing a well with a 50% water cut, you need much higher PWF to flow your well, so your requirements are higher than your available or the deliverability of your reservoir, and then the two curves are not intersecting each other, and in this case, you cannot produce your well at these parameters, and for this case, you need a supporting artificial lift method to be able to produce your well. The same, of course, is happening when you are producing with 90% water cut. So the requirements of the system is much higher. So the two curves of the VLP and the IPR are not intersecting each other. And so you cannot produce your well. And someone would ask me why, if you are increasing the water cut or choosing different water cuts, why the IPR is being like this 3 curves. However, it should be just one curve, because the water cut, if it changes, if it changes, so supposedly no change inside the reservoir, but Prosper considers, unlike other softwares, let's be honest with you, Prosper is simulating the different water cuts and its effect on the IBR, as it considered higher water cut is having lower gas and lower compressible fluids inside the flow. And so the pressure losses will be lower. And so your absolute open flow will be higher and your pressure losses, total pressure losses inside the reservoir are less than normal case. So I am suggesting that this curve, this red one, will be the higher water cut. And as you can see, it's PWF, it's absolute open flow, and its deliverability is bigger than other curves until reaching the zero water cut. So this is nice. Let's choose another case to make sensitivity on. For example, let's simulate on the productivity index, okay? Productivity index, we have chosen our case to be 1.5. Let's choose 0.5 and 2, and 5, for example. 5. Okay, click on done. Here are the cases. Calculate. Never forget to calculate, okay? Okay. If you are producing with 0.5 productivity index, so your operating point is around 600 stock tank barrel per day. Producing with 2, of course, the results are much higher, 2,500. And of course, with 5, let's see what happened. You cannot produce. Let's see the plot, what it tells us. It can tell you that your results are much higher than your scale or limits of the production. So you cannot produce both curves with the requirements of the VLP, or this tubing cannot handle all these amount of curves. And as you can see, there is no intersection point. So this violet curve is 2 productivity index. And you can see, if you are extending this line, you can see the absolute overflow much higher than this curve with 0.5 productivity index. And of course, you will have this IPR, which is 5, and you have just one VLP curve because the productivity index is not affecting the VLP. So you will have just one VLP and 3 different IPRs. Click on finish. Let's choose another case, which is, for example, the solution gas oil ratio. The default one in our model was 600. Let's choose it to be 600, 1,000, and 3,000, and then done. And calculate. Okay, at 600 SCF per stock tank barrel, you can be producing this figure. At 1,000, you will get higher flow rate, and at 3,000, you will get a higher flow rate. Let's plot this. All cases done. Okay, you can see obviously that the system has drawn 3 VLP curves and 3 different IPRs. The same reason for drawing different IPR is the same as the water cut. Prosper considers that the change in the gas rate and the GOR and the changes on the water cut, they are highly affecting the IPR or the pressure losses inside the reservoir. Okay, and of course, as I have told you before, the GOR has the same phenomena of tubing. You are producing to a limit with a higher GOR. يعني if you are producing with a higher GOR, you will be producing a higher flow rate. But up to limit, and after that, the friction losses will be dominating the total pressure losses inside your system. And after that, the results will be inversed, and you will be producing lower flow rates. Okay, this is يعني a roughly summary of the of simulating an oil well, drawing the IPR, drawing the VLB, and see the intersection point between the same, and then applying some sensitivity analysis and different variables on the system, and see the effect of all these variables on the operating point and the solution node pressure. This is just an intro to Prosper. Of course, in Prosper, you have a lot of models to simulate, like oil well models, gas models, different kinds of artificial lift methods. You can simulate multi-layer models. If you have different perforations with different depths, you can enter also in the model, and you can simulate this and see the commingled flow will be how. Prosper gives you a lot of solutions and a lot of models you can simulate with a lot of correlations for the IPR and VLP and for the choke performance. You can simulate all your system and take all the data. And of course, you can do match cases to compare between the simulation results and the actual results. And after that, you can do some adjusting for the enter data and choose the best correlations that represent your actual data. And after that, you can apply it to the other well modeling inside your field or the offset wells. This is for now. If anyone has any question, I will be happy to hear from anyone.
Thank you, Engineer Amr, for this fruitful session. I really enjoyed it a lot. And of course, Prosper has so many features, and inshallah, we will discuss most of them in our next live course, which is titled Integrated Production Optimization Using Nodal Analysis. That will start next Sunday, inshallah, presented by Engineer Amr. We will now be able to receive your questions through the chat, or if you want to open the mic, please raise your hand and I will let you open the mic. Okay, for the first question, what is the difference between solution node and top node?
What is the difference between the solution node and the top node?
Yeah.
So easy. The solution node is the node at which you choose your node. يعني in our case, it was the bottom hole node, which is the PWF. But the top node is usually the wellhead pressure or the downstream pressure after the choke. And you can also choose your node to be the top node. يعني in some cases, you can choose the wellhead to be your node for solving this. And in this case, the segment before this top node, which is from the reservoir up to the wellhead, it will be just one segment, and the pressure losses will be calculated for all this segment. Okay.
Okay, thank you, Njam. We have another question from Lala. Can you talk about skin?
Okay, in Prosper, Okay. What I have explained for you today was just an intro to an oil model. But of course, Prosper has many correlations to count for the skin. For example, let's see from these correlations. Let's choose, for example, Darcy. In Darcy, he will be asking you more data to enter, like the reservoir model. He will be asking you the reservoir permeability, thickness, drainage area, shape factor, and well radius. And in this section of the geomechanical skin, it will be asking you the mechanical skin. If you know the exact figure from the drawdown and build-up tests, you can just enter it in your model. And if you don't know this figure exactly, you can simulate it by different techniques. For example, on this left, you can choose enter skin by hand or use Caracas and Tariq method, and it will open for you another window to enter the data you have about the perforation and the deviation and the invaded zone, encouraged zone, and a lot of the data. And of course, this needs much more time to talk about. It will be not finished in one session, but I can tell you honestly that Prosper can simulate all of this. If you have all the data, it can simulate for you the actual theoretical data of your well.
Okay, thank you. Another question. Let's assume that we acidize the well. Can I assume that the skin will be equal to zero? If we make an acidization, can we assume the skin to be zero or not?
Okay. Usually the skin is zero for a virgin well. Usually, as we know, that the skin value is ranged from negative value to zero to positive value. The negative value means that your well is stimulated and you have higher permeability and higher productivity, the higher productivity index than the virgin reservoir. Okay, if you have positive skin mm, resulting from the perforation, the the brine or completion fluid. So in this case, your skin will be positive, and we assume that zero is for a virgin reservoir. So after stimulation with acidizing or with hydraulic fracturing, you can see that your skin will be negative. And if you know the productivity index, we can do sensitivity analysis in different cases and enter the productivity index and see the changes in the flow rates and the flowability of the well. Another thing is that you can see from here, you have a dedicated tab for stimulation. You can enter the data of the hydraulic fracturing or acid stimulation and then simulate on them and see the output data of the software.
Okay, someone is asking, in our case, was the triple SV subsurface safety valve located at 150 or not?
150, yes.
Okay. So any more questions? Please, Zidane, can you elaborate what do you mean by this parameter is the same for case or open hole? Which parameter? Do you mean the skin? Okay, until Zidane answers, we have another question. Which stimulation techniques can lead to negative skin factor?
All the simulation techniques, if they are done properly, they can lead to a negative skin factor.
Okay, so any more questions? Okay, I think this is all for today. Thank you, Engineer Amr, for this wonderful session. It was really beneficial. And thank you all for attending. This is a kind reminder of our next live course, which will be starting this Sunday, titled Integrated Production Optimization Using Nodal Analysis, where we will discuss most of the Prosper and pipes and features. Thank you.
Thank you all. Nice to meet you, and let's meet again. Thank you. Bye bye.
Thank you soon, and see you soon, inshallah, in our next webinars.